Welcome back. Let us start the third lecture of week 2. In the first two lectures of this week, we have tried to explain to you the reasons why the properties of nanomaterials are quite different from those observed in their bulk counterparts. We have given you the reasons of this modulation which is observed or modulations which are observed in the nanomaterials based on quantum mechanical treatment or free electron model which combines the classical picture with certain assumptions used in quantum mechanics, and both could explain the property modulations in nanomaterials. So, let us continue with the discussion and see what happens to another fundamental aspect of these solid nanomaterials, that is the impact of size reduction on the crystal structure of the material. We have seen the 1D lattices, 2D lattices, and how do they vary from the 3-dimensional lattices. Clearly, the number of atoms, how these atoms are arranged, and what are the relations between the positions at which these atoms can be placed in a crystal lattice can have significant impact on the final property of a material. So, we must understand how the crystal structure gets modulated due to size reduction. For that, we will first give you a brief overview of the various types of crystal structure. What do we understand by symmetry? What is 2D Bravais lattice or what is a 3D Bravais lattice? You will find that there are various types of Bravais lattices. We will give you a brief overview of this, and then we will move to the point of size dependent structural behavior in nanomaterial. How does this structure change? Because if you see that phase transitions have mostly been explained using the changes in thermodynamical parameters which are temperature, pressure, and to some extent volume and entropy. But we will show you that size reduction can also induce phase transition. There is also a very interesting point which I must talk to you at this point, that sometimes people ask, what is a phase? Just define phase. Phase is something which is defined as physically distinct, chemically homogeneous, and mechanically separable. That defines the word phase. So, you should be able to have clearly different physical properties within the same molecular unit type material. For example, just before we end this lecture, I will give you a few examples. For example, we will talk about gold, but then we will also talk about a very interesting and a well studied material like barium titanate, which is an AbO3 type structure, that is a perovskite structure. and while maintaining the molecular unit means what? AbO3 here it is barium TiO3. So, barium titanate. It is one of the most useful ceramics which is available to us in today's world, and its derivatives. Some dopants are used. So, for example, barium strontium titanate is used in memories, sensors and relaxer ferroelectrics, chemical sensors, capacitors. So, it is a very well understood material, but it can undergo phase transition as a function of size reduction, and how does it impact its properties will be discussed. So, we will talk about phase transition and the stability of the phase, and then we will talk about the implications of this modulation or modulations and the applications of the materials. So, we have already seen in earlier lectures that how we define lattice. It is a periodic arrangement of points in 1, 2 or 3 directions, giving rise to 1D, 2D or 3D lattices. But please remember, a crystal lattice also has an additional point attached to it, which says that it is a lattice which will show translational and rotational symmetry. That means, if you have atoms placed at one point after the other, then as you have a translation motion, each and every atom will find the same environment around it. And if you have a rotation around that atom, you will again find that the environment will remain the same. These two additional points are essential to define a crystal lattice. It is not that one atom has to be placed, you can actually put a group of atoms at each point. So, it is not that you have to put only one atom, but you can put a group of atoms and then repeat those group of atoms at different lattice points, and that will give you now comes the next point, which says what is a unit cell. A unit cell is the cell when it is translated in any direction can fill the complete space without overlapping. Without overlapping, this is critical. That is why the unit cell is called the building block for a crystal lattice. So, one unit cell, then the next, then the next, then the next arrangements form together, and then you can just repeat it one after the other. It can be of any volume, size or orientation or even shapes, but it will follow certain symmetric rules if you are talking about a crystal lattice which has crystalline nature. So, it is not that everything is random. Once I say that it is a crystalline material, either single crystal or polycrystalline, the arrangement would follow certain specific symmetric rules. We will talk about that in next few slides. And the primitive cell is the smallest volume cell which is there, and it can then follow the translational vectors A and B, and you will get the points where atoms are placed. So, how do you differentiate one lattice from the other? If you see, the first term we have been talking about is symmetry, and you have another term which is called as point operations. That means symmetry is around a given point. What is the symmetry of the atom? And then you have translational is given by one aspect, and then rotational is given by another aspect, and that is around an axis. In this case, the axis is given here, and you rotate around this axis, and that gives you rotational symmetry. So, a circle, for example, can be rotated around an axis passing through its center through any angle, and then you will get back the circle. But what about the other shapes? Let us see a square. So, you have a square which is placed like this, and then you have a axis. Rotate the square by 45 degrees. What will you get? You will get this arrangement. Rotate it again by 90 degrees, that is with respect to this, you will get the square again. Similarly, you can have for rectangle, rotate by 90 degrees or rotate by 180 degrees. So, you can see how the structures rearrange just by rotating the structure about a axis. Now, there are various angles through which one can rotate an object. However, please remember, I am emphasizing it has to be consistent with the translational symmetry to make it a crystal. Why? Why is this point so important? For example, if I have a barium titanate unit cell, BaTiO3 unit cell, which is placed at different lattice points. Now, barium titanate has, for example, 8 barium atoms, 1 Ti atom, and you have in all you have 6 oxygen atoms, but the contribution to a given unit cell for barium is 1/8, titanium is complete, oxygen is half, and therefore you get a molecular unit of BaTiO3. So, you have one BaTiO3 unit cell. Then you go to the next unit cell. Question is, can you differentiate between one barium atom from the other barium atom? No, you cannot. They are identical. That means one unit cell, then the next unit cell, then the next unit cell are all identical. So, I can choose origin at any given point in a lattice, and therefore, as I move from one point to the other, I should have the same environment, because each and every unit cell, if placed at a given lattice point, must see the environment same around it, so as to ensure long range ordering and fulfill the criteria of being called as crystal. And that is why translational symmetry means moving from one point to the other, as we cannot differentiate between the unit cells. Therefore, the environments should remain the same, and that is why translational symmetry is so critical. I hope the concept why translational symmetry must be maintained is clear now. So, let us see a figure and define the angle and do the corresponding calculations if you have two dimensions which are given as per the figure. Clearly, you will find that sine of alpha minus 90 is Cc dash by A, and from there I can then move on to calculate the value of cos alpha. Now, you can go on putting any values of p, fine, very good. Just randomly we will put some values. Let us say we have range from minus infinity to plus infinity if possible. But when I do that, you will clearly see that there is a range in which cos and sine can range. It is plus minus 1. Beyond that, cos and sine are not defined, and therefore, if I have values beyond that, then they have no physical significance. So, for example, I have p is equal to minus 2, cos alpha becomes 1.5, alpha, is it defined? No, and therefore, this symmetry which is 360 by alpha, how much angle I want to rotate, cannot be defined. Minus 1, yes, I can then define alpha is 2 pi. You rotate the structure full once 360 degrees, put p equals to 0, you will get alpha as pi by 3. So, you will get 360 by 3 and you have the corresponding symmetry which will be there. Then you have 1, 2 and 3, put those values and you will get the corresponding rotations. So, you can have 1, 2, 3, 4 or 6-fold symmetries. Question is, can you have 5-fold symmetries? Answer is no, if you are not talking about structures like fractals or so. But for typical crystal structures which have the definition which we are talking about, then you cannot have 5-fold symmetry. With this concept, can you prove why 5-fold symmetry is not possible? And it is a very easy and simple exercise which you must complete if the points discussed to you are clear at this point. So, let us see. Clearly, by choosing different vectors, you can then construct various types of unit cells in 2D crystals. You can have square lattices, you can have rectangular lattices. Here, what have we changed? We have kept the angle as same, but we have changed the values of A and B. You have centered rectangle lattice, we have added an atom at the body center, that is at the center. Then you can have hexagonal lattice or you can have an oblique lattice. So, you can have different combinations of A, B and the angle. Similarly, you can have the 3D crystal structures. You can have either primitive type, body centered cells, face centered cells, or base centered cells. Body centered means along with the edges you also have an atom at the center of the body. So, for example, let us draw it and hopefully the things will become clearer to you. This is incorrect. So, if there is an atom here, so you have an atom at the body center. But if I draw a face center, then what will happen? Then there is an atom at the center of all the faces in addition to the atoms at the edges of this cube, and similarly base centered. So, you want in base centers what will happen? You will have only at the base, not all the faces. So, you can then have various combination. 3D structures mean you have A, B and C as lattice parameters and alpha, beta, gamma as the angles. So, you can have various structures as example triclinic, monoclinic, orthorhombic. Just see the variations in alpha, beta, gamma along with A, B, C. Or you can have tetragonal, cubic, trigonal or hexagonal. So, if you take the combinations, all these combinations together, you will get 14 Bravais lattices in 3 dimensions. So, generally with so many combinations you have an idea that okay, it would be an infinite combinations which will become available to us. No, if you have to follow the symmetry rules, then there are only 14 combinations which become available to us in 3 dimensions also. So, it is not an infinite combinations. So, even in a 3 dimensional structure you have only 14 Bravais lattices. So, you can then see certain examples. This is body centered cubic, there is an atom as the body centered. This is what we had shown to you. You have a face centered cubic, example NaCl. So, there is an atom at the center of all the faces. Now comes, so you can clearly see that you have A, B, C as lattice parameters, alpha, beta and gamma as the angles between the 2 axes A, B, B, C or C, A. Till now we have been defining these crystal structures which are having unit cells in the dimensions of let us say angstrom. So, A can be approximately let us say 5 angstrom or so. Similarly, B can be 10 angstrom or so, C can be 10 angstrom or so. This is unit cell, but it is not a particle. In a particle you have a large number of unit cells coming together and then you see 1 mole have how much? Avogadro's number of particles. Now these are arranging. So, you have a large number of atoms forming one particle, and therefore, you have a dimension which is large. So, one unit cell is small, but it is a building block, large number of unit cells come together to give us a particle. Question is, let us say all these unit cells come together and give us a particle which is 100 micrometer in size, let us say one of the dimensions. And now we are taking this dimension to 100 nanometer. This is what we are talking about. How does the property change of this structure when we are just reducing the size? You will find that the property variation is driven by the fact that there is a change in surface to volume ratio, there are quantum confinement effects, and the surface energy dominates. Because of these factors, you may get lattice distortions, altered unit cell parameters, or even stabilizations of metastable phases or a new crystal structure altogether. Let us talk about surface energy and surface stress first. What is happening in a nanomaterial? We have seen that more number of atoms are actually coming to the surface. The counterpart, that is bulk, you had lot of atoms in the bulk also and on the surface, but here the number of atoms which are there in the bulk are eliminated because you are reducing the size. So, and this structure is now enforcing a condition where most number of atoms are coming on the surface. On the surface means what? It does not mean that they can leave the surface. There is still energy, that is the image force, which is forcing the atoms to remain intact at their points without leaving the structure, and the overall material has to remain stable. If you talk in the same lines, means if the atoms are on this surface, they experience unsaturated bonds. The atoms on the surface, if you see the bonds, they are unsaturated because there are no atoms outside that, that is the top surface. So, that means these are having higher surface energy. So, please remember, a system will only be stable once I minimize its energy. So, to minimize the Gibbs free energy, the structure has to readjust. It may not change totally, that it goes to a new crystal structure, but it has to rearrange to start with. Thermodynamically, this can be explained as the Gibbs free energy given as the Gibbs free energy in bulk plus gamma A, where G is the total Gibbs free energy, gamma is the surface energy per unit area, and A is the surface area. We have seen in spherical particles, if you take this, surface area increases as if A by V, if you take the surface area by volume, so 4 pi r square by 4 by 3 pi r cube, you will get the term 3 by r. So, if r decreases, A increases. So, surface energy terms become significant and structural phase that has the capacity to minimize this energy, even if it is in a metastable state, becomes more favorable. So, just because surface area is becoming larger, you are forcing the structure to readjust so that it can minimize the energy. So, if you talk in terms of lattice parameter modifications, now you are changing the structure. So, for example, A minus A naught by A naught, that is the change or the stress along the A direction which you are introducing. A and A0 are not same, and therefore, you are introducing strain on the structure. So, lattice constants deviate from bulk values. Generally, lattice contraction occur because the surface atoms exert an inward force. Why? Because if you exert a pressure or force outwards, what will happen? The atoms will start leaving the surface. That means you are going out of the crystal. That is not allowed. It is a material which is stable, and therefore, they have to feel an image force inside which is directing inwards, and therefore, you have a contraction effect taking place. This is typically an example for gold. So, you can see a contraction in the range of 0.5 to 2% in comparison to bulk. So, if as 1 by r square increases, that is as size decreases, the lattice constant A0 decreases. Now comes what we had discussed earlier. You have quantum effects, confinement effects, and they can modulate the electronic band structure, which can directly affect the equilibrium of the lattice, and because of that you can have symmetry breaking or distorted crystal phases. Because of this modulation in energy levels, you can have metastable phases, or you can actually have stable phases which are different from those that you observe in the bulk. Let us say TiO2 polymorphs. If you see the structure of TiO2 in bulk, it is rutile, but if you take it to smaller size, it changes its nature and gives you an anatase phase which is different from the rutile phase. And this is not only for TiO2, it can be in iron oxide, it can be in zinc sulfide, it can be in gold, it can be in aluminum oxide. You can just see that the structures go on changing just because there is a size reduction, and the corresponding reasons can be lowering of surface energy. You can have a combination of surface energy minimization plus magnetic ordering, which we will talk in terms of elongated grains in later part of this lecture series. You can have surface energy effects, you can have stress induced phase transitions or modulations in the crystal arrangement, or just because you want to minimize the energy, you will go to a new crystal arrangement. Similarly, you can find that the melting point decreases due to instability in crystal structure or size reduction. Smaller nanoparticles show lower melting points. This is because the lattice which is forming has weaker binding energy, and this means that you can have phase selective synthesis of nanomaterials, you can have enhanced catalytic activity, you can design and fabricate new types of electrochemical materials or even magnetic materials. Let us see an example of barium titanate which I mentioned earlier also. Barium titanate is a very well investigated material. If you look into the bulk of the structure of barium titanate, it undergoes 3 phase transitions. If you come from high temperature to low temperature regime at around 130 degrees, it goes from cubic to tetragonal, then at 5 degree it goes from tetragonal to orthorhombic, and around minus 90 degree C it goes from orthorhombic to rhombohedral, and this is the corresponding dielectric constant curve. But if you see the bulk, so which has a structures like this, cube or sphere or large structure, so they are large size particles. You make nano size particles, for example these are hollow nanostructures of barium titanates, and take the corresponding dielectric constant curve. You will see that the phase transition at 130 degrees, that is cubic to tetragonal phase transition, is totally suppressed. Here you were getting a peak at 130 degrees, but here you are just not seeing 130 degree peak, that peak is shifted to around 50 to 60 degrees, but the peak at around 5 degrees it is more prominent than that observed in bulk, and the one at around minus 90 is also quite insignificant, but if you zoom it you will find there is an evidence of structural reorientation at minus 90 also, and it does not show any frequency dependence. If it is not showing any frequency dependent variation in the dielectric constant, it means it is a structural phase transition and not a relaxer type phase transition. So now just by changing the size you have changed the region at which the dielectric constant of a material will change. So if now you want to use barium titanate with a fixed dielectric constant in the range of let us say 100 to 150, you can use nano size particles because its dielectric constant is not changing. But if you use the same material and you choose the dielectric as barium titanate to be operated in capacitors in the range of 100 to 150, you can see even a small change in temperature goes on changing its dielectric constant, and on all your electronic calculations go on changing, and therefore the capacitance is changing, and hence the corresponding voltages which you thought you would get are going to change just as a function of slight temperature, and therefore you cannot use that kind of dielectric if you are making a capacitor which has to operate in the range of 100 to 150 or 100 to 200. So just by changing the size of the material you can suppress the peaks, that is the variation in dielectric constants, and you can modulate the corresponding applications of a ceramic material. You can use these references for understanding more about this topic, and I hope in today's lecture you could understand how the crystal structure changes as a function of size reduction, and size reduction can have serious impact on the properties of the material, and we took some examples today like stress, strain, melting point or dielectric constant. So I thank you for attending today's lecture.